Hello and welcome to Tim Talks Space. This is our chance to talk to Tim Peake about some of the exciting things going on in space. Hi Tim, how's things?
Hello, good morning everybody. Good to see you, Jeremy, and great to be back for another Tim Talk Space. I'm really looking forward to this session. Should be good fun.
Fantastic. This time we're going to be talking about worms in space. Sounds a bit weird, but we've got an expert with us. This is a professor from Exeter University, Tim Etheridge. Hi Tim.
Hello, nice to see you. Hi,
Tell me, you're a professor of integrative physiology, I think.
You're promoting me. I'm not quite a full professor yet, but thanks. I'll take the promotion. Yeah, integrative physiology is essentially a posh word for using a term for saying we study from molecules all the way up to man. So the very smallest chemicals that regulate essentially how we behave as a whole organism, human.
Okay, thank you. Now, it's going to get really confusing having two Tims on the line at once. Tim Peake, you were in space for 6 months. In your crew, you were with somebody called Tim Copra. So you've had this before. How did you cope with that? Did you have nicknames for each other, or what did you do?
Yeah, we actually spoke about it because Mission Control were a bit concerned, and they were saying, do you want to be called by nicknames or call signs? And we said, you know what, I'm sure we'll work it out. If you want to do an initial call, Tim P, Tim K, then after that, it becomes quite clear who you're talking to. And it worked out just fine, actually.
Oh, jolly good. Well, there's no clues there then. I was wondering whether we needed to call you Tim Astronaut and Tim Worms or something. But we'll do the best we can and try to avoid confusion. Anyway, online, we've got some experts to help answer questions. So do ping any questions in the chat, and we'll see if we can answer them as we go along. We'll bring out one or two of them if we can while we're talking as well. So, Tim Etheridge, what do you do then for a living?
I'm a researcher at the University of Exeter. I divide my time between Earth-based studies to try and understand what regulates physiology, the way we work, and a fair chunk of time's committed to doing spaceflight-based research.
Fantastic. So what's all this about worms then? Why on earth are you sending them into space?
So believe it or not, this is kind of the usual question, of course, and it's a fair question, because worms are surprisingly potentially an excellent model for how humans behave, both in normal health and in disease situations. And the same is exactly true of spaceflight. So we know that in all organisms examined to date in spaceflight, including worms, they display the same sort of changes, both at the molecular level all the way up to the whole body changes. And worms are no different. And so because of that fact, we can use worms to try and study those precise causes of those harmful changes that occurred to the human body in space.
So it's particularly muscles, I think you're looking at, isn't it?
Yeah, that's the primary focus of most of my research. And indeed, muscle decline in space is one of the most prominent and frequently observed changes that occurs to people like Tim Peake in space. He may say otherwise. But because of that fact, and because muscle is really important for keeping us healthy in general, so if we lose muscle mass, not only do we move more poorly, but it also affects our overall health, our metabolic health. So we're more likely to become diabetic, obese, and other nasty things that are chronic health problems. So the idea being that if these astronauts continue to get these changes in space, it's a bad thing. So we want to try and stop it.
So it's going to help astronauts and it's going to help people on Earth as well. So do these worms have big muscles then?
It depends how much they exercise train, I suppose. No, they're 1 millimeter long, so they're microscopic animals. Their muscles, though, although size is a kind of a subjective topic when it comes to worms, their structure, the way they work, all those chemicals that regulate the way they function is extremely similar to humans. Surprisingly so for a 1 millimeter long animal. So again, it's another reason why we can understand stuff about humans by studying worms.
So Tim Peake, why or how do astronauts lose weight in space? This is a question from Macron Chouaib, who sent it in last week.
Yes, yeah, great question. And just to follow up on what Tim said, yeah, we never saw any of the worms on the exercise devices there, but I'm sure they found their own ways of keeping fit. But how do we lose weight and lose this muscle mass? Well, really, it's due to weightlessness. Our body is just not working so hard when we're in weightlessness. Everything is relaxed. All your muscles go to the most relaxed position. Your shoulders come up. There's no gravity pulling you down. And so that means that our muscles, if you don't use them, you lose them. And in some of the early shuttle missions, 5 to 11 days, NASA were saying that astronauts were losing up to 20% of their muscle mass in just that short period of time. Now, we've managed to reduce that massively thanks to our knowledge and our understanding now about exercise and how important exercise is in space to stop that muscle mass deteriorating. But it's more than just the muscles, because the muscles are attached to the bone. And the other thing we've realized is that how much our muscles are important to keeping our bone strength and stopping our bones from deteriorating as well. So that exercise has been vital to understanding and trying to prevent that, much as Tim has mentioned about the research about worms.
So there's a few questions have come in about all that. Chloe Louise Bond wants to know how exercise feels in space compared to here on Earth. Is it easier to run for longer, for example? Do you get the same muscle ache, or do you fatigue slower? It's a good question. And do you prefer exercising in space or on Earth? And then Penny Rowan has asked, which types of exercise or bits of equipment ended up being the most useful in offsetting the effects of being in space for 6 months?
Yes, well, I mean, we've ended up using a variety of different exercise devices over the years because we're trying to learn more about what exercises we need to do. For example, there's a picture there of me on the running machine when I ran the London Marathon. And running in space is a little easier on your legs because that harness that keeps you attached to the treadmill can only generate about 70% of your body weight. And so you haven't got 100% of your body weight on your legs. But actually it's very narrow, and you're having to carry all of that body weight on just your collarbone and a little bit on your waist as well. So I'd say it's easier to run, in terms of your legs, but actually it's harder on the overall body. But we've tried using bungee systems. We've got a bike machine there, which is great for really giving us a good cardio workout. You can really get, a high heart rate on the bike machine. We've also got an ARED machine, which is where we do our muscular workout. And what's really important is understanding and identifying the different types of exercise that stimulate the best muscle growth and the best bone growth as well. And it's that bone muscle interaction that we've worked out. Actually, if you do high intensity workouts for a short period of time, that's where you get the best results.
That's useful for us on the ground as well. I think that's what we're always told as well, isn't it? That machine looks like it must be making the whole space station rock. Doesn't it disrupt some of the experiments on board?
So that's the ARED machine, and no, it's isolated. So it's completely floating, if you like, on joints which are articulated, so that we can actually, work out with high weights, heavy workloads, without affecting the microgravity environment of the ISS. It's a really, really clever device. And what our training experts down on the ground do is they give us a protocol. So over the 6 months of our mission, we will gradually increase the intensity of our workout. We never plateau, because if you plateau, then that's when the muscle loss is going to start. That's when the bone loss is going to start. We're always increasing the intensity every week, just to make sure that we're working at the maximum that we can in order to stimulate that bone growth and stimulate that muscle growth as well. So, I mean, the ARED is a really nice machine to work out on, and actually it feels good. When you're floating around in weightlessness, it feels quite nice to put weight on your body again, weight on your legs, and to actually do some squat thrusts and feel that weight going through your spine. It's almost nice to have that compression again that we're so used to here in gravity.
Well, we've got some questions about that. There's a question from Oscar from Frogmore Junior School, who wants to know how you cope with gravity when you get back to Earth after not having much for so long. Does everything feel really heavy? But there's some related questions, so we might as well ask them all at the same time. Gregor, who's 12, and Annabelle in Kent ask, after your return to Earth, had your body weight reduced due to changes in bone density and muscle? And how long did this take to reverse to pre-flight levels? And then William Balthazar, who's 8, from Solihull, wants to know, did you have to do weight training when you got back to Earth to get your muscles back used to walking again? And Sophie wants to know, when you were back on planet Earth, how long was it before you felt normal? So I think they're all related questions there.
Yeah, and it's a very true point. When we get back, everything feels heavy. Yes, you've been out of Earth's gravity for a long time, so just holding something like an iPhone or a tablet, feels very, very heavy. And you imagine your entire body when you lay down on the bed and you put your head on a pillow, everything feels heavy. You feel all those pressure points on a bed, for example. So we do have to go through rehabilitation. About 3 weeks is ideal to do that initial period to get our muscles back in shape. And the areas where we really miss gravity on our body are places like our quadriceps, our calf muscles, our lower back muscles, our neck muscles. These are the muscles that you don't even realize right now, whatever you're doing, whether you're sitting down, standing up, these muscles are working all the time to counter the effect of gravity. And in space, they're not working. They're having an easy time. So when we get back down, even though we've been exercising our major muscle groups, it's impossible to exercise all those small stabilizing muscles that help keep our skeleton in shape and intact. And that's what our physios are trying to do. They get us to do these strange exercises during that rehab phase where we're working the core, we're working our lower back, and we're rebuilding all the muscles that we weren't able to exercise in space. I thought I felt pretty good after about 2 months back on Earth. I would have said I'm back to normal in terms of what I can do. The flight surgeon said no, 6 months. They say it's a day for a day in terms of the recovery period until you're completely normal. And bone density takes a lot longer than that. We're losing about 1.5% of our bone density every month in space, and that's even with exercise. Now, you consider that an average adult who's over the age of 50 loses about 1% per year. And that can lead to osteoporosis in an elderly population. So to lose 1.5% a month is quite significant. And as soon as we get back to Earth, all of that weight loading and the training that we do is helping to stimulate our bone growth as well.
At least I guess bones isn't a problem that the worms have to worry about too much. But tell us a bit more about them. Where on earth, Tim Etheridge, do you get your worms from?
Well, they originated just up the road from here. They were first discovered on a rubbish tip just up the road from here in Bristol. And they were quickly established as one of the best in vivo systems for studying human disease on the planet. So, yeah, they're quite local to us.
Wow. So it sounds like you've had the same lot that have been going into space for a while. Is that right? Or do you have different lot each time? Same
ancestry. So they're basically hermaphrodites. They're both men and women. So they produce these genetically identical children. And so, yeah, they keep cycling the same genetics down and down and down through their children. But then ultimately we're sending mutants, basically, just like X-Men mutants into space. So some of the worms we're sending are pretty much the equivalent of me to say Tim or Arnold Schwarzenegger or Usain Bolt, these very different high achievers. Are kind of the mutants that we're sending into space versus the average Joe like me.
So who could have expected the original worms that they found in Bristol to become the ancestors of a whole family of spacefaring worms? Is that really exciting for them?
Yeah.
How do you grow them so that there are enough to do your experiment?
They need basically the same thing we need. They need food and they need oxygen. And so provided we give them food to eat and enough air to breathe, they do pretty well. Except that food isn't a fillet steak like I quite enjoy. It's bacteria and E. coli. Not the sort of E. coli that'll hurt you. It's been changed to be non-harmful to humans, but they basically eat bugs, eat bacteria.
And how did you get them to the launch site?
In a plane, in a very expensive shipping company to keep them cold. So we don't want them to dry out. We don't want them to starve. We don't want them to get stuck in United States Customs for ages in a nice hot room baking away. So we pay a company to make sure they arrive nice and safely to launch site.
And then how do they get into space? Do you have to send them with an astronaut handler, a worm wrangler?
Not too far off, basically. A lot of customs forms.
Do they mind the launch conditions?
You'd have to ask them. I don't know. I imagine they wonder what the hell's going on during launch. But
So here is the launch. I think we can see now. So what rocket was they launched on?
They went up on a SpaceX Dragon capsule.
So there were no astronauts on board that, but
No.
it's presumably Tim Peake, the same capsule that you'll be travelling in with any luck one day, or you hope
Yeah,
to.
hopefully. And the SpaceX capsule, of course, that provides a pressurized, climate-controlled environment, and so it's the most suitable capsule for bringing up experiments such as the Worms in Space experiment, where you want, a pressurized, climate-controlled environment that helps the specimens come onto the space station in the most ideal form. And yes, I'd love to take a trip on SpaceX in the future.
Do you think that the worms mind the launch conditions and all that vibration stuff?
The vibrations can certainly affect them.
I'd imagine they find it quite interesting during the launch and in the microgravity, getting used to it. But I'm sure they go through the same adaptation period that astronauts do in just trying to work out what's going on and how to live and how to operate in a new environment.
And how long do they live in space? That's the question that's come in from Noah, who's 12 years old.
For me, that entirely depends on the experiment, but in this case, it was only 5.5 days. So their life cycle was quite short. And so in 5.5 days, we can study most of the sorts of things that we would study in a human between about 18 to 20 years old up to their sort of 40-year-old sort of range. So that 5.5 day window is enough for us to study a single generation of animals and how spaceflight affects them.
And how does microgravity affect them? I mean, this is a question from Patricia, who's also sent that in. She's 16 years old and from Germany. She wants to know how they behave in microgravity.
Yeah, again, much the same way that astronauts do, but on a very simplified scale. All those chemicals respond very similarly. So the molecular differences very closely mirror the sorts of things that astronauts experience. They move a bit worse in certain aspects. They can potentially have worse progeny sometimes. So they certainly do adapt in that short time frame.
So what happens when they reach the ISS then? What actually is the experiment you're doing on them?
So we essentially just need to get them up there cold. So we launch them in cool bags just to keep them at a nice temperature. The capsule will dock with the ISS, and someone like Tim will literally take them out and put them in an incubator for a stable temperature. And we just let the animals do their thing. We don't need any interventions in this particular experiment. There's Alexander Gerst doing our thing, and we literally just need them to live. And then when the experiment stops, we want to stop all those chemical changes that occur in the body from happening any further, so we get a snapshot of time and space. And so they take them out and put them into a freezer to stop all that happening and bring them back to us.
So, Tim Peake, do you want to explain what this device is we're looking at here? Is that too big?
Yeah, I think that is, yes. So Alex will be, controlling the experiment there, running the procedures, and then he'll be using Melfi, the -80-degree freezer, which is where we store all of our samples on board the space station. For example, our own blood samples that we take that need to come down on the next SpaceX. SpaceX is the only capsule that re-enters the Earth's atmosphere and comes back to Earth. All the other cargo vehicles burn up in the atmosphere. And so the SpaceX is very important for being able to bring down the scientific samples. So that's me using the Melfi there, storing some things away, wearing the protective gloves because it is so cold. And as astronauts, we'll be following the procedures. We'll be keen to make sure that we just do everything absolutely correctly, knowing how much time and effort people like Tim have put into this experiment, in terms of working out how to get the samples, what they're studying, how to transport them. The last thing we want to do is to make a mistake.
So people will be itching to know, if you've got a deep freeze there, did you use it to store ice cream? We have to know this.
Well, SpaceX are actually a really friendly bunch, and the first time that we captured one of their Dragon capsules, we opened the hatch, we unpacked the whole module, and there was one box at the bottom, and I was looking through the cargo manifest and I couldn't find the serial number, and I thought we'd made a mistake, and I got on the radio to mission control and said, we have no idea where this box needs to go. And they said, oh, just open it for us and let us know what's inside. So I opened it up and it was full of ice cream. It was just a small sort of lunch size thing, and had the little mini Snickers, mini Mars ice creams in it. So we were very happy about that. But we don't store them in the -80. We've got somewhere else that we can throw those.
Well, it always pays to keep your laboratory assistant happy, I suspect, doesn't it, Tim Etheridge? What Tim Etheridge makes a really good space experiment, do you think?
I think that feeds on from what Tim Pete was just saying, that I think simplicity is key, if possible. It's not always possible. And whereas Tim said he's worried about messing up our experiments, we're worried about using their time because it's so precious. And so the simplicity is obviously not because they can't handle complicated things, it's because their time is so restricted that we want to keep it as simple as possible, like taking a bag, a cassette, and putting it in an incubator, and then that's it. That's a very good situation, and it reduces the chances of error and time commitment.
Yeah, I was afraid you were being rude for a moment then, but I think it's clear astronauts can cope with complicated experiments if necessary, but it's better not to. How many experiments did you do while you were in space, Tim, do you think? Did you actually have a count?
You probably touch about 200 to 250 different experiments in a 6-month period. So there is a lot going on. A whole chunk of those experiments will actually be on your own body. They're the life science experiments, which really follow on from what Tim was saying there about the worms experiments, because we're analyzing the same thing. I mean, I had muscle biopsies taken before I flew and when I came back down, so that my own muscles could be studied to find out the changes that had happened in the structure of them. It's fascinating for us to actually find out as much as we can. We can't become experts in every experiment. We wish we could, but there's just simply not enough time. But the more you enjoy an experiment, the more you get involved in it, then the happier you are on the space station, because it makes it so much more fulfilling. And also we try and have a relationship with the PIs so that we know who they are, what they're trying to achieve, and we know who to go to if there are any questions that we have about an experiment. Some of them are more complex than others. And some of them you might have a real passion about, a burning personal interest that you really want to dig a bit deeper into the science. But ultimately, we are lab technicians. We're following a checklist, we're following procedures, and we're just trying to work as quickly and as efficiently as possible so that we can get through as many experiments in the shortest amount of time.
So presumably the muscle biopsies were to do with muscle deconditioning. What about aging? Did you do aging-related experiments?
We did, yeah. Well, there was one Canadian experiment called T-bone, which was fascinating because I spoke about the bone density reducing, the atrophy there of your bones. And we've realized how to change our exercise so that we try and reduce that. But when we come back, sometimes you could just do a DEXA scan, which is a very basic bone density X-ray. And you might be misled into thinking that you haven't actually lost that much bone. But we've realized that what happens is the bone starts remodeling itself in space. So actually it's the inside of the bone, the structure is reduced and you just end up with a much bigger holes, and the bones thicken on the periphery. So although your bone density might look like it hasn't changed too much, that doesn't mean the bone structure hasn't changed. And this is really interesting to look at right now. We're using high resolution 3D X-ray modeling techniques. So the latest technologies to really understand how our bones have changed in space, and then how they turn back to normal, and what we can do to try and minimize the risks involved.
So I suppose the thing is that as astronauts, you are an example of healthy individuals that have been carefully monitored before, during and after, which is pretty unlike the normal population, where usually we only measure people when they become ill. So I guess this is one reason why astronauts are quite helpful, isn't it? It's hugely helpful.
And the PI involved in the T-bone exercise said in a 6-month mission, he can learn what would take 10 years on Earth. And also, as you said there, we're doing this on relatively fit, healthy young individuals, so we can recover. We can come back and weight train and hopefully, prevent ourselves from getting osteoporosis. But you can't, do the same kind of testing and experimentation on an elderly population who are already suffering from bone density loss. So it is a really good environment to understand the changes on the human body in a short space of time.
Wow. So let's get back to the worms then. So we've done the experiment on them in space. They've been frozen and now they're going to be brought back to the Earth. How do they get back to you in Exeter?
Cold.
Tim Etheridge.
The very key requirement there is that they stay cold. If they come back a bit warm, then it's ruined everything. So it's really important that we get active cooling on the way down. And then there's much in the same way that we paid a lot of money to get them shipped to America in the first instance, we pay a lot of money to keep them cold to come back to our lab. And that's job done then. We can all breathe a sigh of relief.
So it sounds a bit like making an ice lolly in space and then trying to keep it frozen all the way back from orbit back to America, across the Atlantic, and then from wherever it lands in Britain to your offices or your labs in Exeter. That's quite a trek for an ice lolly without it melting.
Yeah, and if the edges of that ice lolly melt even a bit, the whole thing's ruined.
Oh, goodness. So then what happens?
Then we just analyze all the molecules in their body, essentially, all those chemicals that we know regulate certain processes like muscle loss, like potentially bone loss in what Tim was just talking about, the way our nervous system works. We can look at whether there's more of them, less of them, they've moved, they're working slightly differently, to give us really detailed mechanistic knowledge about how the worms have responded to space.
So what did you find out? I mean, that's the point of all this. What have you learned?
Well, we've done a number of space flights. So in the past, we know a lot about what we think are the molecules that are changing. This experiment in particular now was an interesting one because we targeted those with new drugs and genetic interventions to try and stop them from occurring, to then have a cause and effect relationship to see whether they actually do cause the muscle changes. And that data is still under analysis. Funnily enough, about 2 days ago, we received all the data back in a massive, great spreadsheet. And so we're just processing that now. So watch this space.
So I guess you spend some of your time in a lab with chemicals and petri dishes and what have you, and part of the time in front of a computer with spreadsheets and data. Is that right?
There's a lot of numbers, yeah. I'd say more numbers than anything else. Fortunately, I'm in a position now where I have people doing all the lab stuff, which is the fun bit. So it's a bit sad for me how I look at numbers.
So you found out a lot of the chemical pathways, if you like, in controlling all this stuff. Why does it all matter?
Because essentially that's what regulates life. I mean, all these, all the way down to the molecular level, if those things are working differently, then that feeds up as a knock-on chain mechanism that ultimately changes the way our muscles contract, the way our bones are healthy, how our brains signal to all the tissues of our body. It's those molecules that are ultimately the root cause of all those endpoint changes that we see and feel.
So it'll be useful to us mere mortals living on Earth. Will it also be useful for people like Tim Peake traveling in space?
I mean, for me, that's the main motivation of doing the flight work, is that if we can understand, and then obviously if we know the precise causes, we can develop drugs and other interventions like ARED that target them specifically. But actually, as Tim was just saying as well, the analogy between space flight and aging on Earth is true of muscle as well, but on a much quicker time frame. So the changes that occur to an astronaut's muscles in a very short space of time are very similar to the exact changes that occur over many, many years in a human on Earth. So it's possible that what we learn from space can benefit older people on Earth.
But I guess when it comes to long duration missions, it will be vital, won't it? Tim Peake, presumably exploring Mars with human beings one day will depend on this kind of research bearing fruit.
It really will. You know, we've got a long transit time to Mars, about 6 to 8 months, both directions, depending on the exact distance between the two planets. That's a long time in a low gravity environment to then have to land on Mars, which has its own gravity about the third of Earth. So you still then have to get out and be fit and healthy and operate. So the more we can prevent bone and muscle degradation during that space flight, then the healthier the crew will be, and also the longer that we can spend in space. And the other thing about your Martian spacecraft, we don't have the luxury of something as large as the ISS, where we have a whole multi-gym with a-red and a treadmill and a bike machine. We need to compact that into a very, very small, lightweight exercise device. And so the more we can understand about exactly what exercises we need to do, how often, and the intensity, then the better place we'll be for long duration spaceflight.
And we've got a question here from Ollie C from Dawston, who's 8, who wants to know, how long do you think it'll be before we've got humans living on Mars? It's a big question.
Yeah, well, you know, there's so much happening right now. It's hard to put a marker in the sand on that one. I mean, I would say pretty confidently to the late 2030s at our current pace. And I don't think it's going to be slower. If anything, I think the advent of working with commercial companies and the timelines that those commercial companies are working on, and other nations as well, if anything, it's going to drive that date forward, not backwards. So, you know, we are already well established for returning to the moon in the next few years and establishing a permanent base on the moon. And I think then the next stepping stone will be the 2030s, where we'll see the target focused on Mars.
So I guess if Ollie is 8 years old now, he's exactly the right sort of age to be aiming to get into training for visiting Mars, don't you think? Absolutely. Yeah, that's what's so exciting about the new generation. You know, that's going to be beyond my career time frame, but yeah, people watching this, absolutely a well placed to become our first Martian explorers. Well, let's try helping them. We've got a question here from Estella, who wants to know, does it matter what GCSEs you choose to do, and are there any out of school activities that kids can start to try to prepare for a possible career in space travel? So any thoughts on that?
From my point of view, I think what's more important is about finding out what you're passionate about and trying to be as good as you can be. It does help if you have a background in science, technology, engineering, maths. Everything that we're doing on the space station tends to be around science and technology. It also helps if you're familiar working with other cultures and other languages in an international environment. They're the kind of skills that you can pick up later in life. Nobody leaves school and becomes an astronaut straight away, so it's not something you have to worry about initially. But if you do enjoy science, technology, mathematics, then they're great subjects to be studying.
Brilliant. So Tim Etheridge, coming back to you then in your career, what was it that, how did you get into it? What did you study?
I'd love to say that spaceflight was always on my radar, use a pun, but it certainly wasn't. So I did the old equivalent of a BTEC in leisure and tourism, of all things, and an A-level BE. And then I went and did sport and exercise science at Brighton University. And it wasn't until after that I just started doing basically research. I just did something I enjoyed, and it led down this path. So, I mean, much like I think that Tim was just saying, I think STEM is obviously crucial, it's really important, but I think if you just do what you enjoy and you do fairly good at it, then I think these opportunities open up. And so when these spaceflight opportunities came along, I was in a good position to apply for them and try and be involved, and it all snowballed from there.
And I guess you always work in teams. Here's a picture of your team. Which one are you? I can't quite work it out.
No idea, but yes, an international thing. So we brought on people from all around the world: South Korea, Japan, the US, Greece. So a multinational team of researchers we brought on board, all with their own questions to be asked, and it was a fascinating experience working with all those guys. A lovely bunch.
So it sounds very similar to what Tim Peake was saying about being good at languages is just one of the things you might not have expected if you're going to go into a career in space or in science.
Yeah.
What's the thing that you love most about your job?
Just the new experiences, just doing interesting things, finding out obviously new knowledge that is hopefully ultimately beneficial to people somewhere down the line. For me, all of this would be pointless, spaceflight included, if I couldn't see an end point where it might benefit someone like Tim in space or an elderly person on Earth. I wouldn't be bothered doing any of it. So that's what I find genuinely passion inspiring for me.
Fascinating. Well, I guess we all have the same sort of motivations, whether you're an astronaut or a space scientist. Or do you even count yourself as a space scientist? Maybe you don't.
No, I mean, I am. I can't escape the fact, but it probably is about a third of my research program, but probably takes up 2/3 of the time.
But I guess for most of us, that's probably the case as well. And most people going into jobs in space in this country are working partly in space and partly on the ground doing other things. Unless, of course, you're an astronaut, in which case you probably nearly everything you do is space related.
Absolutely.
Right, I think we're going to have to call it a call time now, because I think we've had a bit more than half an hour. So thank you very much for your efforts there. If you at home would like to get involved, we've got some great things that you can do at home. So first of all, the Worms in Space experiment. Tim Etheridge, do you want to tell us what's available if you go to your website?
Yeah, absolutely. So we really push the outreach and activity side of things. So we developed some resources for school children of different age groups. So if they go to the MME-Space Worms website, there's all the archived resources on there, and people can learn about the experiment, why we're doing it, and ultimately, when we get those results, we'll start to make them accessible on there too.
And we'll have the link on our website. We've got an educational resource page, which you can find in the top right of the homepage. And I think we've got the link also somewhere down here. Mission X, Tim was an ambassador for us while he was in space. Mission X, trained like an astronaut. Fun to do at home. We've now got 36 different countries taking part in it. I'm thrilled at how many people are doing this. We've got, I think it's about 50,000 people across the world taking part. So lots of physical coordination and science activities you can do related to staying fit and improving diet and so on, but all related to how astronauts do these things. So maybe have a look at that. And anything else on our website, we've got lots more ideas for you to look up there. So join us at the same time on the 13th of July, when we'll be doing the last in our current series, I'm afraid, of Tim Talk Space. We're going to take a summer break, and we're going to be talking about exploring Mars. So please do join us then. So in the meantime, thank you very much for watching, and thank you very much, Tim Peake, and thank you, Tim Etheridge.
Thank you, Jeremy. Thank you, Tim, and thank you to